Good day students. In this video we are going to design a combinational circuit to find 2's complement of 3-bit number. So if you see 2 complement of any 3-bit number will be a 3-bit number for except 0. So we have assumed that 2's complement of 0 is 0. So for an input 3-bit number, we will be having 8 different combinations from 0000 to 111. Let us start our designing. So here we are having 3 inputs and 3 output, and let me name the 3 inputs as Z, X, Y, Z and 3 outputs as ABC. So there are 3 inputs, so 8 combinations. Let me write the combinations. So the combinations will be from 0000 to 111, and the output is the 2's complement of the input. So if I consider 001, the 2's complement of 001 is 1's complement plus 1. So the 1's complement is 110. If I add 1, the 2's complement of this 001 will be 111. So similarly, we can obtain the 2's complement for each and every combinations here. So the 2's complement of these combinations are: for 000 we have assumed 000, for 000 111, for 010 110, and for the next combination 101 100 011 010 001. So ABC represents the 2's complement of XYZ. So you want to design a digital combinational circuit to find the 2's complement of any number. So if you input this as into your digital circuit, you should get this as a output. So here we are having 3 inputs and 3 outputs. So we have to consider one output at a time, and we have to design a circuit for A independently, and then we need to design for B separately considering the same inputs, and then we need to design for C separately. So here we will be having 3 different problems. So we have to draw 3 K maps, and we need to find the expression for A, B, C separately, and then we have to draw a circuit incorporating all the 3 expressions. This truth table can be minimized into a simple function like this. So one output A with the inputs X, Y, Z is equal to sigma of 1, 2, 3 and 4, and B with the input X, Y, Z is equal to sigma of 1, 2, 5 and 6, and C with the inputs of X, Y, Z is equal to sigma of 1, 3, 5, 7. So we have framed 3 problems, and we need a 3 variable map to solve these 3 small problems and to find 3 expressions. So to find the expression for A, we need to go for a 3 variable map where the inputs variables are X, Y, Z, and the values are 0, 1, here 0, 0, 0, 1, 1, 1 and 1, 0. So the block values here is 0, 1, 2, 3, 4, 5, 6 and 7. So filling out the min terms here, the min terms for A is 1, 2, 3 and 4. So to obtain the expression for A is equal to, we need to group these ones. So the minimum number of groups that can be formed by combining all these things. So this is one group and this is another group, and this one cannot be grouped with any other ones, so it is grouped separately. So for the first block we get an expression x bar, and it is expanded row wise to get this x bar, and when it is expanded column wise, the non-changing variable is z, and the value of the variable is z. So x bar z for the pink one, and for the green one, if you extend it row wise, the value of x is 0, so you have to consider x bar, and if you expand column wise, the value which is not changing is y, and the value is 1, so you have to consider x bar y. And for the separate block, here if you expand it row wise, the value is x, expand column wise, the value is y bar z bar. So the expression for A is find out by considering these momentums and find the appropriate things. Similarly, we can find the expression for B and C. So for B, we can draw a similar mapping with similar variables, and if you fill the minterms, you will be getting the minterms in the locations 1, 2 and 5 and 6. So these are the locations, and if you want to group this one, these two can be grouped once and these two ones can be grouped. So the expression for B will be equal to, for this group x value is varying here, so leave the x, and if you expand here, the value of yz here is 0, 1, so this is y bar and this is z. So the expression is y bar z. So for this yellow, if you expand it row wise, x is changing, so for the column, the value of yz is 1, 0, where y is taken as it is, and the minterm for z is z bar. So the expression is y z bar. So the expression for B is y bar z plus y z bar. And similarly for C, if we draw the K map, you will be filling the ones in space 1, 3, 5 and 7. So this is 1, 3, 5 and 7. So for grouping, these ones are covered, so these 4 ones can be grouped as such. So the expression for this C will be equal to, this particular thing is expanded here, so x is changing, so leave x. When it is expanded column wise, here it is 0, 1 and 1, 1. So here the non-changing value is only z. So C will be equal to z. So we have determined the expression for ABCs. So as a final point, we need to draw the circuit. So for drawing the circuit, we need, let be x. So x is given to inverter to get x bar. Y is this. Y is connected to inverter to get y bar, and z is here, so it is connected to z bar. So all these values are inputs. So based on these inputs, now we are going to draw the diagram. So for A, the value first is x bar z, so it is taken from x bar z, and it is given to a AND gate. And the next term is x bar y, So I am taking x bar and y, and it is given to AND gate. The third term comprises of x, y bar and z bar. So all these AND gates output are given to OR gate. So the final expression is A here. So similarly for B, we will be having y bar z as a first term. So we will be taking y bar z as a first term. And the second term is y z bar. So we will be taking y z bar. So this is the second term, and it is connected to a OR gate. So all these expressions are in sum of product forms, and we will be getting B for here. And C is taken directly as from Z. So Z is directly taken and it is named as C. So all these components, so these form our digital circuit which we need to build to implement this circuit. And hope you can understand the things. And thank you for your patience.